presentation will be done by Dr. Mahidhar Tatineni from San Diego Supercomputer Center. He received his MS and PhD in aerospace engineering from UCLA. He currently leads the user service group at SDSC. As a computational and data science research specialist manager, he has led the support of high performance computing and data application software on several NSF and University of California funded HPC and AI supercomputers, including Voyager, Expanse, Comet, and Gordon at SDSC. His research interests are in HPC architecture and systems, performance and scalability, benchmarking, and HPC middleware. He has worked on many NSF-funded optimization and parallelization research projects, such as MPI performance tuning frameworks, hybrid programming models, big data middleware, and application performance evaluation using the next generation communication mechanisms of emerging HPC systems. He's the co-PI of the NSF-funded Expanse HPC systems and also the National Research Platform projects at SDSC. So he will actually join remotely. Mahidhar, are you online? Let's bring him.
Thanks, DK. Yes, I'm online.
Yeah. So let's give a big welcome to Mahidhar.
So I'm sharing the presentation. Looks okay?
Yes, we can see the slides.
Okay, thank you. So I'll get started.
Your video is not turned on. If you would like to, you can do that.
Can you see me okay now?
Yes.
Okay, thank you. I'll be talking about our experiences with MVAPICH and INAM on the SDSC systems. The talk's a mix of what we've done in the past and what's coming. So hopefully, I think as you saw with Dan's presentation, a lot of our relationships are very long-term, over decades. And so I'm going to talk about a little bit of what's already happened and also the upcoming system. So the outline of the talk is essentially a brief bit on MVAPICH on Expanse. I'll generally talk about the system architecture and how actually it's grown over the past few years. So and then talk about a few of the applications that use MVAPICH on Expanse. And then go on to INAM usage on our systems. We have it installed on, we had it on a system called Comet that just very recently retired, and also are in the process of getting it set up on Expanse. So I'll talk about INAM on our systems and give an example from Comet in the past year where we basically used it to debug a performance issue and actually reconfigure the system. So that is a good use case. I think last time at MAG I had talked about just installing INAM on Comet, and we had probably given a couple of slides on the network topology and stuff, but from then on, actually we used it to debug issues and things. So it was a pretty interesting use case. And then I'll talk about the upcoming systems and expansions. So Expanse will have additional 2 racks coming online later this year. So I'll talk about that. That's going to be part of the AI resource. And also talk about the Cosmos system that will feature the MI300A Instinct APUs from AMD. And Slingshot networking. So I'll give a brief summary of that system. And we expect to be leaning on MVAPICH for all of these systems. So all of that's coming down the pipe. So just MVAPICH on Expanse. So Expanse itself, as I mentioned, has grown. When we first started out, it was a 5 petaflop system with 728 standard compute nodes. Now that's grown to 17 racks from 13 racks, and I'll kind of give you info on what was the growth. And this is our category 1 system from the NSF. We've been over the past almost 4 years serving the NSF research community with computational needs, basically primarily AMD ROM based system, but the newer racks have been Milans, and then we're going to be adding more GPUs coming in the coming year. The main design for Expanse was to have a flexible setup where you would have scalable compute units, and we could add in new resources as we went along into this network architecture. And the way it's set up is we have full bisection connectivity within a rack, which actually, given the number of cores per node and the number of nodes, we have 56 compute nodes in each rack. You have close to 7,000 cores, 7,100 cores within each rack. So for most of our users, that was kind of enough computing power at full bisection that would help out from a performance standpoint. And then between racks, we have a 3-to-1 oversubscription. So that kind of describes the system itself. So we, like on the SSCU, we have basically 50 CPU nodes, each with basically 2 MDA processors. So 128 cores and 256 gigs of RAM and 1 terabyte of NVMe. And then the GPU nodes, original GPU nodes were V100 nodes, and we've since added a few A100 nodes, and we're going to add H100s later this year. And I think I mentioned the switch, so I'm going to skip over that. So the growth of Expanse itself, so the original configuration, it was 13 racks with AMD ROM and V100 GPUs on 52 GPU nodes. And later, NSF funded a path expansion, this partnership for advanced throughput computing. That expansion was 2 racks of AMD Milan with also 8 4-way GPU nodes with A100 GPUs. We also had an industry rack added and a CW3 rack added in the upcoming, basically later years. And then the upcoming expansion is the NAIR pilot supplement that I'll talk about. So MVAPICH has been pretty integral to most of what applications we do on Expanse. There's a lot of different applications that have used MVAPICH. I just have a little flavor here. You can see the range. Basically, you have genomics codes like RAXML, you have quantum chemistry and MD codes, and neuroscience, and of course the machine learning AI kind of workloads. And the MVAPICH team has been involved right from the beginning with the Expanse setup. So we are grateful for their support and kind of have leaned on that all the way through. So that was Expanse and MVAPICH, and I'll talk about when we do the expansion for AI. Definitely MVAPICH Plus will figure into it. So that's a little bit later. In terms of the other part of it is we started looking into monitoring of the IV traffic on SDSC systems. And they're not really any free good tools before INAM to do that in an open source kind of setup. So this was a very good thing for us to try out on SDSC systems. And so basically, it was installed on Comet initially. The system was at that point actually retired from NSF, but being used for the CW3E work. And so we were trying to use the historical and live data to troubleshoot performance issues. That actually they were noticing some bottlenecks, and we were using this tool to monitor that. And because our Lustre traffic also goes over that same network, it was actually an interesting mix of the communication from the codes and then the Lustre traffic, and actually it was impacting both, of course. So the workloads were both I/O intensive and communication intensive. So this was kind of causing bottlenecks, and INAM actually helped us find those bottlenecks and address them. So yeah, the Comet machine essentially at that point was being used for the Center for Western Weather and Water Extremes, and it's essentially used for near real-time forecast during the storm season. And they actually make this data available publicly so people can actually plan for the storms that were predicted. So just a quick overview of what INAM was showing us from a network standpoint. So this is a full system network view. If you remember, the architecture is for Comet also, it's very similar to the Expanse one. It's basically full bisection within a rack, and then oversubscription of, I think, 4-to-1 in the case of Comet between the racks. And you can clearly see the rack level views there. We have 18 nodes per switch and 4 switches at the rack level that feed into the 3 next tier switches. And you can actually see that both on the full network and then the zoomed in here. And then on a single switch, there are 18 nodes. And then, of course, you can go down to the node level and inspect. INAM also integrated with Slurm, so you can actually get a job level view of the traffic. And again, this was helpful with the particular debugging that we are doing. So the way we set up on Comet was to have notifications when the link utilization went above some level. So the idea was hopefully we could identify issues using the notification. So this is an example of what we were able to see from INAM, and go back and figure out where exactly the bottlenecks could be. So for example, if you look at the line in red there, that's actually the connection from the mid-tier to the director switch in Comet. Then you have connections from the leaf to the spine, that's kind of in green there. And then you have connections from the director switch to the Lustre storage servers, all of which basically show up in this. So the OSS there stands for the object storage server. So basically, we were getting these notifications of saturation of the links as the intensive forecast simulation was running. So the IO patterns and load were basically saturating the leaf to spine links. And that was what was showing up in our director switch. And this was actually affecting the IO performance for the NRT run, which actually led to them missing targets, because the way that a whole set of simulations was going on is they get an input kind of set of parameters and observations like early in the evening, and they're supposed to turn around the predictions by the next day morning before, I think, 6 a.m. So you actually had a target to hit with the runtime, and if the IO performance was slow, it would end up actually missing that, because it would slow down things enough that the time wasn't enough to finish up the runs. And so based on these notifications, we are actually able to figure out that, okay, the issue is with the leaf to spine link saturation. And we could actually basically redo the networking so that we move the OSS, the Lustre object storage servers, into the mid-tier switches. So this actually removed the leaf to spine bottleneck, and also kind of balanced out the traffic on the OSS links. So just so you can see, that was the Comet architecture before we made the change. So you had those 72 nodes in a rack, moving on to the FDR mid-tier switches, and then the core director switch. And then the Lustre was actually connected into the director switch originally. So that was causing the bottlenecks that we were seeing. So we changed that so that the luster storage went straight into the mid-tier switch, and that actually fixed the issue. And once we did that, we didn't basically see the OSS links or the director switch leaf spine links in the saturation list. And essentially, the bottleneck was moved elsewhere. I mean, they still have a lot of communication traffic that was saturating the links, but at least it now wasn't affecting the I/O because we were now going directly into the mid-tier switch. So that was a good example of using INAM to essentially fix the network bottlenecks that we were seeing. So right now we are basically working on getting INAM going on Expanse. It's installed on our dev system that basically features the same nodes and same networking. And the architecture is similar with the oversubscription of links between racks. So it'll be interesting to see if we see similar bottlenecks or similar issues on the networking side. Interestingly, on Comet, we hadn't seen the problem till actually we got to the extreme weather scale weather simulations, which combined both intensive communication on the code and the I/O. But it's a good thing for us to look at the monitoring, and we're hoping to get INAM to do that on Expanse. And it a little bit of a change that we use a ClickHouse database server and the C++ interface for that. As I mentioned, we're going to have new GPU racks added later with NDR InfiniBand. So INAM should be useful in monitoring the cluster, and hopefully we can do that with the mixed IB types that's going to be in the system. So let me see. So moving on to the upcoming systems and expansions. So the first thing is Expanse will have additional racks. So this is the Expanse AI resource. So this is going to be essentially new GPU computing and storage capacity that will be integrated with Expanse. It's coming later this year. And the resources will be made available to the National AI Research Pilot Project users. This is essentially 2 scalable computing units with 17 GPU nodes per rack. And each of these nodes will have 2 36-core Intel Sapphire Rapid CPUs, 1 terabyte of memory, and I think 6.4 terabytes of node local NVMe, and 4 H100 GPUs per node. So I think that's a total, if I do the math right, is 168, if I'm not mistaken, GPUs that get added to Expanse. And as I mentioned, it's going to be NDR InfiniBand and 2 NDR cards per node. So the expansion is essentially to enable researchers to train complex models and apply it to like a wide range of applications. So weather prediction, image classification, NLP, healthcare, software development, smart manufacturing, and so on. So we expect like MVAPICH2 will be pretty useful in scaling up these sort of workloads, and we'll be testing that out once Expanse gets these additional racks. It should be later this year. And then moving on to our newest system, Cosmos. This is a Category 2 testbed system that I'm a PI on, and co-PI Suba, Andreas, Igor, and Christopher. And this is going to feature the accelerated processing units, the MI300A accelerated processing units from AMD. So this is a Category 2 system which is structured in 2 phases. There's a testbed phase of 3 years where you can do code development, migration, optimization, and so on. And we are targeting a lot of community codes and some of our user base from Expanse to port over and see if we can get more applications using accelerated computing. And then there's an allocation phase of 2 years where it will be allocated like a regular system. So let me go to the next one. So the goal of this system was to essentially ease the pathway to accelerate a wider range of applications. The enabling technology is the AMD Instinct MI300A APU. The key thing being it has both CPU and GPU capable in the same chip and with unified memory. So we are hoping that this will facilitate an incremental programming approach so that it will ease the porting of applications and help a lot of new communities to adopt GPU acceleration. The compute, it's an HPE Cray EX2500 platform with HPE Slingshot interconnect, 4 socket nodes with AMD high-speed interconnect within the node. And then it's fully liquid cooled. And there's flash-based storage that we're going to have. I'll talk about that in a little later side. And we have already identified a lot of different applications from AI, astronomy, neuroscience, molecular biology, structural engineering, and so on. And we're going to target community codes where possible so that we can amplify the impact once we port something. So the MI300A architecture itself, it's as I mentioned, it combines CPU, GPU, and memory on one package. And basically, there's going to be 6 accelerated compute dies, XCDs, and 3 chiplets with 8 Zen 4 cores each. So you end up with basically 24 Zen 4 cores in each of these chips, and then 6 essentially GPU capability units. And then 128 gigabytes of HBM3 memory that's shared coherently between the CPUs and GPUs. And there's a 256 meg AMD Infinity last level cache between the XCDs and the CPUs. So the design will hopefully eliminate the need to do host to device data copies and ease code development. That's where the goal was to make using accelerators easier. And within a node, typical node, basically there'll be 4 of these MI300A APUs. There's going to be the AMD's Interchip Global Memory Interface, XGMI, providing the connectivity between the chips. And each APU will also have an associated 200 gig Slingshot NIC, which will provide connectivity to the Slingshot interconnect. And then it all fits into a single rack of EX2500. The compute chassis basically provides power, cooling, system control, and for 8 blade slots. And we have 3 of these chassis per rack and 8 blades per chassis. So that's kind of, and it's a fully liquid, 100% liquid cooled system. So that's all going, the infrastructure is going into the our machine room right now. If you visit SDSC now, you'll see a lot of panels taken out as we are doing this update underfloor to actually support liquid cooled systems like this. So the full system details, essentially it's 42 nodes, each with 4 APUs, so 168 total APUs, Slingshot technology. We'll have storage from VAST, roughly 300 terabytes, maybe a little bit more than this in the final setup. And then we will have additional 5 petabytes of Ceph capacity storage and Cumulo storage for a home file system. And the full suite of HP software tools and system management tools to handle the system. And as I mentioned, we are aiming to support a wide range of applications. So APU memory architecture hopefully will make that easier. Our tagline was no code left behind. Basically, we're hoping that we can get more people on. As I mentioned, we've already contacted several different research groups who will hopefully hit the ground running as soon as the system's online. So just to summarize, MVAPICH2 and MVAPICH2 GDR, we've been using this on expands for several applications. We've used INAM on Comet and actually successfully identified hotspots and bottlenecks that were causing luster file system issues under load. Expanse install testing is going on right now. We basically recabled and confirmed performance in case of Comet. Now on the coming soon category, basically we have the 2 GPU racks to be added to Expanse, and hopefully MVAPICH Plus will be useful in scaling up the expected deep learning application workloads. And then the new Cosmos system featuring the AMD Instinct APUs with Slingshot. Again, I'm expecting to have an MVAPICH Plus implementation. I know they've already got Slingshot support, so that's another thing that we'll investigate during the testbed phase and make available to all our users. So overall, over the years, we've been using MVAPICH for all our systems, I think going back 12 years probably, and hope to continue that in the future. And I'm open for questions.
Thank you, Mahi. Any questions for Mahi? Oh, there's a question, Mahi.
Okay.
So I think you mentioned that you chose the APU architecture and to get the benefit out of the the shared memory capability between the GPU portion of the APU and the CPU portion of the APU, because essentially they share the memory.
Yes.
But don't you get the same kind of memory sharing capability even with the discrete node architecture, as long as you have a AMD CPU with the Infinity Fabric connected to the AMD's, for example, MI300X high-end GPU, and with that configuration, still I think you can share the memory. You can provide the shared memory concept between the CPU and the GPU, and also you may get much higher GPU performance with the MI300X. Type of a high-end GPU. So, what else? The benefit you are to take with the APU type of system.
So is that actually? I mean,
Infinity Fabric they provides the cache coherency between the GPU and the CPU. So in that way, from software's perspective, you just have access to the memory on the CPU side or the GPU side.
Is it directly addressable from both sides?
I think so.
That's
what the cache coherent fabric really means. It's just like NVIDIA's NVLink. If it connects I don't know what other CPU provides the NVLink, but so if the CPU provides the NVLink to the GPUs of NVIDIA, then through that cache coherent network,
I mean, because this
you can have access to the other guy's memory. You can implement the software to do that.
So that might add some latency, maybe. I don't know if there's some additional layer involved.
Well, there may be some latency, but again, it's not exactly the same. It's just a different type of a package.
Correct. Yeah. So I mean,
from the high-level software's perspective, I don't think just a few more clock cycles between the GPU and the CPU doesn't matter that much.
Yeah, from a high-level software perspective, it might be okay, but I'm thinking because there's this last-level cache here that's shared, there might be performance implications.
Yeah, there might be a different optimization point.
Correct. Yeah.
Depending on the platform. Again, that's why I'm asking. Say if you have a.
I mean, that's part of what we have to investigate, I think, during our test bed phase to figure out, like, what are the benefits and things. So this category 2 system is meant to kind of test out things. So, I mean, this is a pretty unique design. And if we do see performance benefits because of this kind of architecture, I mean, that's our goal to kind of figure out what happens.
Great. So with this, we can thank the speaker, please.
Thanks.
So we have a coffee break right now. So we'll resume again at 11, please.